Welcome to the deep dive. Today, we're looking into something pretty complex but fascinating. How engineers actually simulate things breaking. Material failure, fracture mechanics.
Yeah, and specifically, we're diving into a source that details a really neat computational method to do this. It's a finite element implementation.
Using something called the phase field method.
Exactly, for brittle fracture.
Yeah.
And the goal here, our mission, is really to unpack how it works, the core ideas, and maybe some surprising challenges that pop up.
And what's wild is how it's built. The source emphasizes this whole thing as pure Python. Just standard libraries, NumPy,
Yeah.
SciPy, nothing exotic.
Right. And get this, each example they show, it's less than 500 lines of code.
That's tiny. For simulating a crack ripping through a material, that's less code than setting up a simple website sometimes.
It really underscores the aim here, making this advanced simulation technique, well, accessible, educational.
Okay, let's dig in. Why this method? What's the big problem with the traditional ways of simulating fracture using finite element analysis, FEA?
Well, traditional FEA really struggles with the crack itself. A real crack is a sharp cut, a discontinuity in the math.
Like a literal boundary.
Precisely. And when that boundary, that crack, moves or grows, the underlying grid the simulation runs on the mesh, it has to be rebuilt. Constantly.
Ah, the infamous remeshing problem. I've heard engineers complain about that. It sounds computationally expensive and just messy.
It is. It's often the biggest bottleneck. It's hard to automate well. That's where the phase field method, PFM, comes in. It sidesteps that whole issue.
What's the trick?
It introduces a new variable, usually called phi. Think of it as a damage indicator. But instead of being sharp, it's smooth.
So not a clean cut, but more like a gradient, a fuzzy zone.
Exactly like that. TFA goes smoothly from 0, that's perfectly healthy material, all the way to 1, which means fully cracked, completely broken.
Right.
And because it's smooth, this damage field can spread, it can branch, cracks can merge, all without ever needing to rebuild that underlying mesh. The grid stays fixed.
That is clever. Smooths out the problem, literally. So you mentioned it's based on minimizing energy, using something called the AT2 model. What does that mean for failure?
Minimizing energy is, well, it's fundamental physics. Systems tend towards their lowest energy state. Cracks form and grow along the path that releases the most stored energy.
The path of least resistance.
Pretty much. The AT2 model is just the specific mathematical rulebook they chose for how energy relates to this damage field, A-phi-res, and how that damage sort of diffuses. Minimizing it just ensures the simulation follows those physical rules.
Okay, but now the material stiffness depends on this damage field, fire, and the stress depends on the deformation.
Which means everything's linked. The displacement field and the damage field depend on each other. You end up with what's called a coupled, nonlinear system of equations.
Which sounds difficult to solve,
Yeah.
especially if you're aiming for simple Python code.
It definitely is. That's a major challenge.
So how do they tackle that? Solving this complex, coupled, nonlinear beast while keeping the code accessible, for learning purposes.
They made a key choice. They prioritized robustness, maybe over raw speed. They used something called the alternate minimization algorithm, or AM algorithm.
Alternate minimization. Okay, sounds logical. How does it work? Is it like solving one part then the other?
That's exactly it. It's often kind of a staggered approach. You break the problem down. First, you pretend that the damage field is fixed, frozen in place, and you solve for the displacements, the elastic deformation.
Okay, solve for stretch and squash.
Right. Then you freeze those calculated displacements, and you solve for how the damage field should evolve or change based on those stresses.
And you just bounce back and forth.
You repeat that cycle. Solve displacement, solve phase field, solve displacement, solve phase field, until the changes become tiny, until it converges to a stable solution.
That makes sense for stability. It avoids tackling the whole coupled mess at once. But wasn't there a big physical problem with the basic PFM idea? Something about compression.
Ah, yes, the major pitfall. You see, the standard PFM formulation, mathematically, it doesn't really care how the energy gets into the material.
Wait, so you mean if you just squeeze the material, like in compression, the basic math might predict a crack forming, which is obviously wrong for brittle stuff like glass or concrete.
That's exactly the problem. It would allow cracks to grow purely under compressive stress, which isn't physically right. So they absolutely had to implement a fix. They used what's called a hybrid phase field model.
Hybrid model, how does that work? How do you tell the math ignore the squishing part?
It's quite elegant, actually. They perform an additive decomposition of the strain energy density, fancy term, but it just means they split the energy into two parts. one caused by tension or stretching, and one caused by compression or squishing.
Okay.
Split at the energy calculation. Then, the crucial step, the degradation function, the part of the math that lets the damaged material actually grow, they apply it only to the tensile energy part.
Ah, so only the pulling energy contributes to making the crack grow. The compression energy is still there, but it doesn't feed the damage.
Precisely. It effectively tells the simulation, cracks grow from tension, not from pure compression. And that's essential for modeling anything that bends or has mixed stresses, which is, most real-world situations.
That sounds absolutely critical.
Yeah.
Makes the difference between a useful simulation and just a math exercise.
Couldn't have put it better myself.
So they built this system with the smooth field, the staggered solver, the hybrid energy fix.
Yeah.
How did they test it? The source mentioned 3 examples.
Yeah, they went step by step. Started simple. First was just a rectangular bar, pulled at one end, pure tension.
The classic textbook case. Why start there?
Because you have exact analytical solutions for that. You can calculate the peak stress, the failure point, on paper. So they ran the simulation and checked, do the numbers match the math? And did they?
They did. Good agreement. It validated the basic setup, the AT2 model they chose, and it also showed something interesting about that model.
Oh, what was that?
It showed this sort of nonlinear increase in stress before the final break. Because the AT2 model diffuses damage a bit even before total failure, the material softened slightly. It wasn't just a straight line up to the peak stress.
Okay, so it captured that pre-failure damage effect correctly. Makes sense. What was next?
Example 2. A square plate, but with a little notch cut into one side, then pulled in tension again.
The notched plate, another classic. What were they testing there? Stress concentration.
That, and comparing results to other published simulations, like from me and others, again, they got good agreement. But the really key insight here was about a simulation parameter the user has to set, the time step size. They used a pseudo-time delta Taylor.
The time step, how finely you slice the simulation time. What did they find?
They found it mattered a lot, especially right when the crack starts to really go. That onset of fracture is super fast.
A sudden event. Exactly. If you chose too large a time step, delta t, the simulation would just sort of skip over the true peak load. It would underestimate how strong the plate actually was right before failure.
So you needed tiny time steps to accurately capture that critical moment.
Yes. Smaller steps gave a much more accurate picture of that peak force. It highlights a practical issue. Even with robust methods, user choices like step size can really impact the results. You have to be careful.
Good point. Which leads to the third test, the 3-point bending test. Sounds like the final boss for that hybrid energy model.
It really is. You have a beam supported at the ends, maybe with a notch on the bottom, and you push down in the middle.
Right. So you get tension on the bottom where the notch is, but compression on the top surface and near the supports.
Loads of compression. So this test directly challenges that hybrid model. Will it correctly propagate the crack only from the notch tip upwards in the tensile zone, or will it incorrectly form cracks in the compression zones?
And the result?
Success. The simulation showed the crack growing just as expected from the notch, driven by tension, while the compression zone stayed intact. No non-physical crushing failures.
That perfectly validates the need for that energy split, that decomposition we talked about. Without it, the simulation would have been garbage for this common scenario.
Absolutely. It proved the implementation wasn't just mathematically sound, but also physically realistic under complex loading.
Okay, so the method works. It's physically sound, uses simple code. But you hinted at a catch. This is where it gets really interesting, right? The convergence crisis.
Yes. This is the downside of that simple, robust, alternate minimization solver they chose. Remember the back and forth, solve displacement, solve damage?
Yeah, the staggered approach.
While it's stable, it turns out it can become incredibly slow, computationally expensive, right when things get interesting, precisely when the crack actually starts moving fast.
A bottleneck appears just when you need speed the most. Let's see the numbers. How bad was it in that simple bar under tension example?
Okay, so for most of the simulation, before the crack really took off, it would converge super fast, like less than 2 iterations of that back and forth cycle, 2 loops.
Very efficient.
But at the single simulation step, where the fracture started propagating rapidly, step 50 in their run, the number of iterations needed to converge suddenly jumped to 82 iterations.
Whoa, from under 2 to 82. Just for that one critical step, that's a massive spike.
Huge spike. Computational whiplash, as you said. And remember, that's the simplest possible case.
Uh-oh. So it got worse in the notch plate example with the stress concentration.
Oh, yes. Significantly worse.
Yeah.
Because the changes are more localized and intense near that notch tip.
Okay, hit me with it. What was the peak iteration count there?
Using their recommended smaller time step, delta 2.01 at the onset of crack propagation in the notched plate. The AM algorithm needed a peak of 405 iterations to converge.
405 iterations just to calculate one step forward in time as the crack starts. Wow.
Yeah. 400 loops of solving displacement, then solving damage.
So the big takeaway here, the so what, is massive. That simple, stable AM algorithm, while great for learning and ensuring it works, becomes cripplingly inefficient right at the crucial moment.
Exactly.
If you tried to use this exact code for a large, complex engineering problem, say a whole airplane wing or a bridge component that's spiked to 405 iterations, would mean hours, maybe days of extra computer time just grinding through the moments of failure initiation.
It highlights the classic trade-off, doesn't it? Implementation simplicity versus computational performance. The AM algorithm works, it's robust, it's relatively easy to code, but it crawls when the physics gets intense.
Okay, so let's recap. We've seen this elegant phase field method in action via a neat, self-contained Python code. We understand the smooth damage field, the robust but slow staggered AM solver, and that absolutely vital hybrid energy split to handle compression correctly.
And we've pinpointed its Achilles heel, that dramatic slowdown, the explosion in iterations right when the crack decides to go.
Which brings us nicely to our final thought. Knowing this AM algorithm is the bottleneck, what's the obvious path forward? How does this elegant educational tool evolve into something genuinely powerful for research or industry?
Well, the path is pretty clear based on this and related work. You have to ditch the staggered AM scheme for solving that nonlinear system.
Replace it with something faster.
Exactly. Implement more efficient, often non-staggered solvers. Things like the modified Newton method, or perhaps even better, quasi-Newton methods like LBFGS.
LBFGS. Has that been shown to help here?
Oh, yes. Other studies focusing specifically on solver efficiency for PFM have shown that switching from AM-type schemes to something like LBFGS can cut the CPU time down dramatically. We're talking factors of 3 to 7 times faster.
A potential sevenfold speedup just by changing the core solver. That's huge. That could turn days of computation into hours.
It's transformative, but there's more. We also saw how sensitive the result was to the user guessing the right time step. Tilde T, too.
Right, you needed tiny steps for accuracy at the critical point.
So the next level isn't just a faster solver, it's smarter computation. Things like adaptive time stepping, where the code automatically takes smaller steps only when needed during rapid changes and larger steps otherwise.
Let the code figure out the step size dynamically.
Exactly. And potentially adaptive mesh refinement, even though PFM avoids remeshing. You might still want a finer grid temporarily right around the crack tip where things are complex, and coarser elsewhere to save effort. Let the simulation focus its computational power geographically as well as temporally.
So moving from user guesswork to automated adaptive control, taking this beautifully simple concept and layering on the intelligence needed for true high-performance simulation.
That's the journey, from an accessible educational tool to a robust, efficient research instrument.
A fantastic look at where computational fracture simulation is heading. Really insightful.